Hello, everyone. I want to talk about a few things from the Serway book for the particular class that we are taking, which is a non-calculus based class related to physics, related to the second course in the two-course series for a particular non-calculus series course. The first class, first course is usually associated with Newtonian mechanics and thermodynamics and fluid dynamics, things of that nature. So largely Newtonian mechanics and thermodynamics. The second course in the two-course series is associated with electricity and magnetism. For the discussion that we're going to do, I want to look at chapters pertaining to the particular class that I'm teaching. And this is actually for anybody that would want to look at this material from the Serway book. The Serway book is excellent, has got excellent coverage. I'd like to look at two chapters and give like a brief lecture, somewhat brief lecture pertaining to the two chapters in the Serway book related to electricity and magnetism, or at least some introductory topics related to electricity and magnetism from chapters 15 and chapters 16. Chapter 15, electric forces and fields. Chapter 16, electrical energy and capacitance. Let's take a look at it. Well, for chapter 15, the way I would look at something like this, they show various ways to kind of look at this. When we talk about charges and some famous equations that can be written in various ways, not all the books are going to write things exactly the same way, and there is, I guess, some leeway as to how important signs are for you, as long as you know which direction motion will take place. Later on, when we talk about work, the signs aren't necessarily very important, provided you know what you're doing. It's kind of a blanket statement to make, very easy statement to make that kind of covers the teacher as well. But if you know that you're putting in positive work to increase potential energy, well, you're putting in positive work to increase potential energy. If from a high potential energy to a low potential energy, a charge is flowing, then there's an increase in kinetic energy and a loss in potential energy. We're kind of going back to Newtonian mechanics in a sense. And as long as you have it, this is the way I've always taught this material, as long as you have the directions in which you are going under control and you know how much energy you're putting in and how much energy you're losing. If potential energy drops, it goes to kinetic energy. So there's a positive increase in kinetic energy. If you lose potential energy in a particular system, you're going to gain kinetic energy. If you lose kinetic energy, you're going to gain potential energy. So the signs don't become a very big deal. In the past, I've tried to discuss things contrary to that, and in my own personal experience, it doesn't mean that I'm right. It can almost be substantially more confusing if you don't go for a gut feeling, kind of intuitive approach to what's happening. This is one reason I'm making this particular film. In other films associated with the course, and those of you who are in my particular course, I do have substantial coverage of problem solving from chapters 15 and chapter 16 from the Serway book. Indeed true. There was just mostly just straight out problem solving. And we'll also do that in person, and the TAs will help you with that as well. But I do have it on film quite substantially. There's a lot of problems there. They can be solved even with a calculus. If you have a little bit of a calculus background, I show you how to do it with a calculus background, but you don't have to know the calculus treatment of it, but it's there for your personal enrichment for future reference. But in the end, many problems are just solved straight out without using calculus at all. And that's what you have to know for this course. And those films on chapter, for example, on all the chapters, have a lot of problem solving for you. That's also the case for chapter 15. Again, chapter 15, electric forces and fields, and chapter 16, electrical energy and capacitance. Well, from chapter 15, let's kind of just give a quick little summary on what's going on regarding all that, you guys. I'm looking right off the summary of topic 15. I think they call it, here we go. They call the chapters topics. I just call the chapters chapters, as you can see right here. it's every bit as valid, to call it, as we said, this is topic 15, and this is topic 16. That's synonymous with chapters, you guys, when we're talking about that. So, not a big deal. I mean, either way, just know topic for the Serway book means chapter, which is what most people are used to hearing. So when they tell you topic, they mean chapter. For topic 15, if you're looking at the summary in the back of the chapter, in the back of the topic number 15, electric charges, insulators, and conductors. Electric charges have the following properties. 1, unlike charges attract one another, and like charges repel one another. That's 1. 2, electric charge is always conserved. 3, charge comes in discrete packets that are integral multiples of the basic electric charge, E, which has a magnitude, the charge on the electron has a magnitude of 1.6 times 10 to the negative 19 coulombs. The charge on the electron is actually negative 1.6 times 10 to the negative 19 coulombs. We're not going to nickel and dime too much with signs, you guys. I tried to kind of do that in one lecture. I've probably done that numerous times over the years. In my judgment, in my experience, it leads to more confusion than help. But that's just me saying that. For a lot of the basic stuff we're doing, if you know what direction something's going to go in, and I said that a few minutes earlier, right? If you know what direction things are going, the signs aren't really a big deal. Be aware they obviously play a role, but if I'm moving a negative charge away from a positively charged conglomeration, it's got very, very much positive charge, it doesn't move, let's say. If I'm moving that negative charge away from that positive conglomeration, it's close to it, and the negative charge is being moved away, it is going to take positive work for you to move it away. Why? Because you're increasing its potential energy. And we'll get into that. It's very much analogous to what you see with gravity, and I don't want to hit all the intricacies associated with gravity. Even there's numerous ways they can discuss things. As long as you know what you're doing at the basic level, you can foresee any problems that are going to be there, and you can get the job done and get it done right. If there is, we'll cross that. I'll say it now, and we'll cross that bridge in a little bit, I guess you could say. If there's a positive charge conglomeration somewhere, a lot of positive charge, and it's not going to move, and you have a negative charge relatively close to it, great. I mean, there is an electrostatic force of attraction between the positive and the negative. Yeah, it's an attractive force. If you move the negative charge far away from where it was initially, it's going to take work to do that. You're fighting the fact that this attraction does not want for that negative charge to leave. You're going to have to put a force and move opposite away from the positive charge conglomeration. You will have to put in work to do that. What does that depend upon? The amount of work depends upon what are the charges in terms of magnitude. If they both have a lot of magnitude and you're moving it very far away, well, the great distance and the great charge magnitudes pertain to a lot of work needing to be done. Once you've moved very far away, and this is more chapter 16 type stuff, guys, just trying to tie a little of this together. This brings us, chapter 16, topic 16, it's related to that as well. The fact that you're moving away like that, you're putting in energy. You're putting in work. What kind of work? Positive work. You moved it far away. What happened? Well, you did work. What's going to happen to your work? Well, let's assume there's no other forces present anywhere in the universe. What happened to that work is you just gave that system a lot of potential energy. You gave that negatively charged particle that you moved far away from the positive charges, you gave it a lot of potential energy. What does that mean? If you let it go, it's going to fly back with great kinetic energy. It's going to increase kinetic energy as it's going back. If that charged particle already had kinetic energy when it was moving far away, it's going to lose that kinetic energy because you're building potential energy. It's a lot like climbing a hill. It's a lot like climbing a tall building. Climbing the tall building or rolling something up a hill, its kinetic energy, both rotational and straight out translational kinetic energy, is going to get dissipated because of the climb. So from there, you're not really worried about the signs. You already kind of know what's going on. as I said, I've been in past lectures, even recent, where I tried to explain that and it did not go very well. Hence the film right now. Hopefully this goes a little bit better. If you would have had the scenario, again, a positive charge conglomeration and another positive charge over there, if you move that positive charge far away, it wants to go there anyway. You don't have to put work to do that. It's just going to fly off. As it flies off with greater and greater kinetic energy, its kinetic energy increases, but its potential energy goes down in the runaway from that. And we'll kind of talk about that a little bit as I'm talking about it now. So again, now, how would you increase its potential energy? Just the opposite of what you did earlier. When I had the negative charge being taken away, I was increasing potential energy. I was increasing the tension in the spring. I was compressing the spring, or I was stretching the spring in a sense. If you want to use the mechanical scenario, when I'm pulling it away, because it's fighting it, and it's going to spring right back. When it's the positive charge and the negative charge in consideration. When it's the positive charge, if it's far away, you have to force it to go close. Doing that, you're compressing the spring. You're not stretching the spring as you were earlier, you're compressing the spring, but it's the same thing. You're giving it more potential energy as you're going to it. So this whole idea, and that's counterintuitive for what happens in gravity when it's always you're leaving the surface of the earth in a sense, and you're giving it more potential energy, and there tends to be a loss in kinetic energy. If I fire something up into the air, a dart gun, it's eventually that kinetic energy is being dissipated in a sense, being lost, I guess you could say, converted to potential energy. Same thing going on here, but this is more positive and positive charge and positive charge. As you compress the positive charge toward the positive charge, you're increasing potential energy. It's a lot like a spring being compressed. With the earlier scenario, you took the negative charge and pulled it away from the positive charge conglomeration. In that case, you're increasing potential energy, but you're stretching the rubber band, so to speak, for the positive and negative scenario. So you're increasing potential energy by moving away, whereas with the positive and positive, you're increasing the potential energy when you move toward it. So get an idea of what's going on here in this positive and negative stuff that's frequently talked about. I'm certainly not criticizing or going against people that say this. They're brilliant. Follow them if you like on this, but I think if you just have a general idea of the magnitudes under consideration and you just say, well, wait a minute. If I'm compressing that spring, we're losing kinetic energy and gaining potential energy if they're both positive. For me to bring the positive closer to the positive, I'm compressing that spring, I'm losing all this kinetic energy, and it becomes potential energy. When I let it go, it fires back really strong. If it's positive and negative, that scenario happens when you stretch the rubber band, so to speak, take the negative away, far away, and that's increasing potential energy, decreasing kinetic energy in that case. So again, that's kind of the situation. Ran into a little bit of a problem. Like I said, last time I tried to discuss something like that, you guys, but this positive and negative, I guess this is what got me to it, guys, and that's it. They're saying E is 1.6 times 10 to the negative 19 coulombs. It's actually negative 1.6 times 10 to the negative 19 coulombs, negative 1.6 times 10 to the negative 19 coulombs, but we don't need to nickel and dime it. The magnitude is indeed equal to 1.6 times 10 to the negative 19 coulombs. That's tiny. It's almost a continuous distribution because the number of charges, as you increase them, they're not, it's almost barely visible to us in a sense. It almost behaves like it's a continuous distribution, but it's not. There really are discrete increments when that takes place, you guys. The force between two charged particles is proportional to the inverse square of the distance between them. That I went into excruciating detail when we did talk about topic 15, you guys. So pretty interesting stuff in that regard. So when they talk about those four properties related to electric charges, insulators, and conductors, electric charges have the following four properties, as we said, once again. Number one, unlike charges attract one another and like charges repel one another. 2, electric charge is always conserved. 3, so you can algebraically sum them, and they're going to be conserved, you guys. 3, charge comes in discrete packets that are integral multiples of the basic electric charge, E equals 1.6 times 10 to the negative 19 coulombs. 4, the force between two charged particles is proportional to the inverse square of the distance between them. The inverse square law occurs in very many places, as we have said. Okay, guys? they talk about Coulomb's law, and they talk about it, and they say it in a number of ways. We're not going to get hung up on. For now, let's just put a big Q, a small q, or you can call the big Q Q1, and the small q, big Q you can call Q1, small q you can call Q2. You put absolute value symbols between them, or you can just say, hey, look, I just want to know the magnitude of each one of those, so it's a positive phenomenon anyway, and I can make it look like this. We're not going to lose a whole lot of sleep in doing some of this stuff, you guys. Again, based on what I just said earlier, kind of referring back to earlier challenges that I've had as a teacher, I guess you could say, and I know the students have had as well. They're confused on some of this stuff. If we know where this stuff is going, hey, the magnitude of the force under consideration, let's talk about what's going on here. There's this force. We have to overcome this force just like we have to overcome gravity, okay, depending on the charge configuration itself. So, I mean, we talked about some of this stuff, and we did a problem last time. I think we did a couple problems related to some of this stuff. There's a whole lot you can say here, guys, and some of this stuff's going to get erased pretty soon. But you can't help but see the mathematical analogy, incredible mathematical analogy related to the inverse square law happening when you talk about gravitational forces. Electrical forces, electrostatic forces mathematically obey the same principle of the inverse square law. Look at the similarity there. Despite names, despite labeling, look at the great similarity there, you guys. They essentially say at some point, if you've got an E field under consideration, and there's a lot of ways we can do this, we've talked about how you could find the force of gravity, and the force of gravity is a mass times g, and g is deceptively got tremendous weight associated with it, if you allow that play on words, I guess you could say. G is the G is the magnetic, G is the gravitational field, and it arises from, you look at, you got G, M, let's just write the M1, M2 is capital M, just like I wrote capital Q rather than Q1 and wrote small q rather than Q2. Let's write for capital M, M1. What was M1, we'll call capital M. What was M2, we'll just call M. And we got this guy right here. And if you divide it by this M right here, you end up getting for all this whole song and dance, as it proceeds, you got G looking, and like I said, we went into this pretty well, I thought, at least one time that we had lectured this thing. The small m goes, you got this, and that'll get you G. Now this honestly varies. If you're not very far from the center of the Earth, it is pulling as though all of its mass is centered at the center of the Earth, pulling from the center of the Earth. So even at the surface of the Earth, you're not a distance 0 away. You're the radius of the Earth distance away from the center of the Earth, as though something's pulling in that manner from the center of the Earth. You got this. Well, that's all really, that's pretty interesting in that regard. That's the same as if you divide by small m here, you've got G equals Fg over m like this. And you can play the game all day long on that. Well, okay. Well, that's, they put three symbols here, meaning that's kind of a definition in a sense. And I guess as you say, this is as well. I don't want to beat this up too much, you guys, but this is definitely of interest. And can we find an analogy going on in the electrostatic sense? Well, yeah, we certainly can. I mean, what we have here is if you took Fe, which is equal to, and there's a lot of ways you could do this here. Let me just kind of leave it here. Let me divide by small q on each side, you guys, if you don't mind. And let me do it with the other one, too. And we end up getting K, Q, Q over r squared, and we divided it by small q, well, looks a whole lot like what I did earlier in the gravitational sense, if you allow me to say it like that. Looks a whole lot like what I did over here. And that's G, that's the gravitational field. Has a lot more significance. It's not, that G means a lot more than I think we commonly think it means, just solving these problems based on the stuff we did at earlier times when we were doing Newtonian mechanics. Well, this whole thing right here, this Fe over G, forgive me, not G, that was Q rather, I'm sorry, over Q is the E field. And that sure looks that E field, Fe over Q, looks a lot like the G field, Fg over M. This is analogous to the Fe, the M is analogous to the Q. Here's your gravitational field, here's your electric field. So just like earlier you were saying, hey, you know what, there's a force associated with gravity, and for some reason my board's not writing very well, but okay, we'll do what we can here, guys. I got some pretty good chalk here. We got this, and this is the mass, this is the G field, this is the charge, this is the E field. And again, the similarities should come across as pretty striking, you guys, when we're doing some of this stuff. Having said that, and I kind of we'd gone into this quite a bit. They talk about a couple other things that I'd like to say, at least from the topic 15 standpoint, and we already had touched upon it, but let's talk some more. Okay, if everybody's all right with this, let me try to look a little more. Mostly topic 15 before we get to 16. We'll take a look at some of the stuff that's there, and we'll see. I'd like to, I think it's a good idea to look at this stuff and then start coming back at me and at the TAs, in a sense, with can we do some real world problems that are given in this great book, in the Serway book. Can we do it? Absolutely. Okay, so they say some other stuff. Conductors in electrostatic equilibrium. A conductor in electrostatic equilibrium has the following properties. Here we go again. We talked about 4 properties earlier related to electric charges. Let's talk about 4 properties related to conductors in electrostatic equilibrium. A conductor in electrostatic equilibrium has the following properties. Number 1, the electric field is 0 everywhere inside the conducting material. The charges will align themselves in such a way that there is no E field present to move the charges any further. They've gone to where they're going to go. Now, if we do something, we can get them to move, but we're going to apply an E field, maybe externally, an E field externally to make them move. Otherwise, that's it. I mean, they've arranged themselves so that there's no E field inside there. So, number 1, a conductor in electrostatic equilibrium has the following properties. Number 1, the electric field is 0 everywhere inside the conducting material. 2, any excess charge on an isolated conductor must reside entirely on its surface. It's got to go to the surface. And that's the furthest it can get away from everyone else. 3, the electric field just outside a charged conductor. The electric field just outside a charged conductor is perpendicular to the conductor's surface. 4, on an irregularly shaped conductor, Charge accumulates where the radius of curvature of the surface is smallest, at its sharpest points, at sharp points. We talked about the electric flux in Gauss's law. Essentially, guys, we talked about flux. Now, you guys saw me make a pretty big, those who are in my class and have dealt with me recently, associated within about a week or so of the actual date of this video right now that we're watching, we talked about the flux, the electric flux, and we kind of had a neat analogy. We had a neat analogy that the flux itself sort of resembled the power that was taking place, the power transfer, the power experienced, let's say at a rock concert, at a particular distance away from the one speaker. There's only one speaker present. It emanates sounds equally in all directions in a spherical sense. What is the, I guess you could say there, what is the power that is occurring, that is to be observed in some sense? The power is, in a sense, everywhere present, but you're not going to experience it as intensely if you're far away from it. But, you know, I guess you could say the intensity, which isn't very big, is indicative of being very far away from the speaker. That's why you're not experiencing a great intensity. But there's a huge surface area, imaginary surface area, being penetrated. So, and when you know how we played that game in that regard, we said the power was the intensity times the area. Well, the intensity times the area was a constant number for our purposes. If you got real close to the speaker, there wasn't a big surface area being penetrated, but man, there was a tremendous amount of intensity, because that same power didn't have too many places to go. It went through a very small surface. If it goes through a big surface, there's not much power associated with one particular, not much intensity associated with any particular location. But the power from which it came was the same in all circumstances. We kind of gave that analogy when we spoke some time ago. That analogy seems to hold up here in a sense too. The flux in the right circumstances, so to speak, and again, this is a lot you can say, a lot you cannot say. There may be an electric field that penetrates a spherical surface, an imaginary spherical surface. The strength of that electric field, the magnitude of that electric field may be a very big number if it's penetrating an imaginary area that's not a big area. As you go further away, the surface area of the imaginary sphere, the 4 pi r squared, as we said in past conversations, if this thing is very, very large, the E field is not very big. The flux is a constant phenomenon. All other things, I don't want to throw exceptions to what could make something an issue. For our purposes here, if indeed there are any, to be honest with you, but I mean, I guess there's things you can do and the E field wouldn't experience it as much. You are, let's say, in a vacuum. There's no other considerations to think about right now, just this one charged particle that is bringing forth E field everywhere throughout the universe. And let's far away, for a very far distance away, there's no other influences happening here. Well, the E field is very, very strong, close, and that penetrates an imaginary sphere of surface area, 4 pi r squared, 4 pi r sub s squared. R sub s meaning radius small. Well, it's penetrating a small surface area. That's a huge E field, though, because there's only so, you know, it's going through one place, and that's a big E field. So, huge E field, small area. If you go further out to an area of a sphere that's 100 times the area that you had earlier, that we just talked about, 100 times the size area means if this is 100 times bigger than before, the E field has to be 100 times smaller than it was before. And that makes sense. The further away you are, the less E field is present. The less influence the E field can have at a distance. Same way gravity has less influence from a great distance as well. So there, you know, I can put an analogy there. They oftentimes just put this to show, you know, it depends on the angle. If there's some other surface under consideration, they're trying to show maybe it just hits at a particular angle. The way that they're measuring stuff regarding that is the angle is always in terms of a perpendicular. So let's say there's an E field, you know, coming right through here. This is an area A. You give the area vector looking like that. You call it a vector. At least you can make up that it's a vector. You got E right here, and this is theta. That's how that's going to play. And again, this is stuff we talked about. I was a little more concerned about chapter 16 regarding this stuff. They do say something of interest, and you know, I don't, you know, they say let's not worry about. You can worry about it as far as if we're talking about a circular phenomenon here. If we're talking about penetrating an imaginary sphere, the penetration is definitely E goes this way in line with A. If there's a 0 degree angle between them. The cosine of 0 degrees is 1, so it's just EA. For our purposes, it's kind of let's throw the cosine out the window for just 1 second and say, okay, let's say it's just going through a sphere. And every time it's, you know, when it is going through a sphere, sphere's looking like this. There's a little bit of an area there. The area vector, delta A, if you want to call it. And then there's the E field. It's right, I mean, I had to draw it so you can see it, but that degree measure is, you know, as we got it here, that degree measure, we say theta is equal to 0. Okay, or 0 degrees, rather, when you're trying to do something like that. So let's look at let's keep looking at some of this stuff and how this plays out. When we do some of these problems, it should work itself pretty well. You can talk about flux roughly looking like this if we got the ideal circumstance of not worried about theta. Theta being equal to 0, it's penetrating an imaginary sphere perpendicular in all directions. So theta becomes 0, cosine of 0 is 1. Let's just write it like this. And then they're saying that that thing that was generating the E field, that thing is a charge Q that's inside the imaginary sphere. It's a charge Q. This is a constant, and that's also equal to this. Well, if you set both of these equal to each other, this is the Q that's on the inside, not on the outside. EA cosine theta, we'll just say EA. E becomes Q over A epsilon naught. Well, okay. So what does that mean? Well, you know, the area under consideration, we did this last time, guys, and why not keep talking about it a little bit? I mean, we got this. A is 4 pi r squared. That's A, and here's epsilon naught, and this is what E is equal to. Well, I don't know. Maybe I can figure out a way to kind of play this game here, guys. I mean, we got this. 1 over 4 pi epsilon naught. That's this, as is. And that's Q over R squared. This thing right here, my friends, is a constant. And we'll just call it K. 4 is a constant, pi is a constant, epsilon naught is a constant. 3 constants multiply together is still a constant. They're not going to get a variable. 1 divided by this constant is itself a constant. We'll call it K or K sub E. Here's a Q, and here's R squared. Now again, you see this written a number of different ways. I don't want to nickel and dime this a whole lot, guys, but again, you can write it like this, and that's Q over R squared. I could look in the book and stuff, guys, but that's not a big deal. The big deal is these are identical. I mean, this and this, which is the same as that. I probably didn't need to rewrite it, guys. I'm sorry about that, but they mean the same thing. Well, heck, guys, I mean, that looks a whole lot. That looks a whole lot like what I did earlier. Remember we said it came out to this. when we said that E was equal to force electric divided by Q, that was the Q over R squared, pretty interesting in that regard, divided by Q here. Well, do the math, here we are. Kind of neat. This is a more general argument, and it gets you some pretty good results. So we talked about that. We were able to make some pretty good sense out of this whole thing. The electric flux through any arbitrary surface, and this is very important. The electric flux phi through any arbitrary surface surrounding a charge, Q, is Q over epsilon naught. This is universal. It doesn't have to be, they wrote it with small q, but the electric flux through any arbitrary surface does not have to be that imaginary sphere. It makes it a lot easier if we look at it with the imaginary sphere. But let's say we cannot. The electric flux through any arbitrary surface is always going to be this is equal to this. Any arbitrary surface. Does not have to be the sphere that we talked about. Okay. And again, I mean, there's in the films, when I actually arranged this in Canvas for my students, and for anybody else watching this, you'll see I do have films related to topic, related to topic 15, related to topic 16. I probably call them chapters 15, chapter 16, and we do a whole lot of problems there. It takes a good amount of time to do it. They are there for you. This will be posted real close to those, especially on Canvas for those looking to do this. So you can go to those problems that we have solved. Okay. So we got a lot, guys. The electrical energy and capacitance. Let's try to do that smoothly. This is always a bit of a challenge, I think. Perhaps, maybe for the students as well. I'm thinking there's certainly challenges sometimes for the students, oftentimes for the instructor as well when they're trying to teach this stuff. But let's look at some chapter 16 stuff, topic 16, and we'll kind of take it from there if we can. See if I can clean up some of this stuff a little bit, guys, as well. Chalk writes really well in some places, but not in others. I don't know that I can do much about that, but let me see what I can do. And the chalk we're using is pretty much top of the line. So given some of the distances we're dealing with, for you being able to see the video and some of the breadth of the space that I'm trying to kind of go through on the board. I got good blackboard space here, but it's not always easily as visible, perhaps, as I would like it to be. So I obviously try to write pretty big, as you've seen in my past videos, and you see on this. Let me see what I can try to do. On this stuff, you guys. Like the top was having a little bit of an issue. Let's see if I can fix it. If anything, it's going to look a little better, but let's see where it goes. All right, guys, let me see where this goes. Let's talk a little bit. All right, let it dry off and see what we can say about it. Okay, so for topic 16, Well, early on, like I said, early on in this entire discussion, as we were doing this, I basically jumped the gun on it, and that's all right. I mean, we're gonna do it again, but we talked about ways you can say certain things. Now, they say, you know, it's kind of a hard call. They make some pretty interesting moves. This whole idea of subtraction and some other stuff we can talk about. Let's just get there. Try to not let this be some of the issue that it can be. Let me. Yeah, like I said, I'm gonna leave a lot of the problems that I've done earlier. There's more than enough background there. I don't want to overwhelm people with that again. You have it. You're going to have it in Canvas for those of you who are in my classes, and anybody, you'll have it. You'll have access to it in places that are posted publicly on YouTube, in fact, and you can see what I've done there. If you acquire the textbook, you should be fine. So, number of ways to go here when we're looking at some of this stuff. Let me try to follow closely what they're talking about sometimes, and sometimes not so closely what they're talking about. And I think within the context of some things, I think more background's given when we meet in person to talk about some of this stuff. But anyway, let's talk. Try to stay close with. I think what's really excellent, everyone. And I've said this from day one about the Serway book. There's great coverage in so many textbooks that are out there, and there's certain limitations. I mean, if they talk about every intricate detail of how to look at something, the book won't be this thick, as I've told people in the past. The book's going to be that thick, so they can't really, and there, I guess that's hopefully where, at some level, the skill of the instructor, the skill of the teacher comes in to kind of say, okay, let's sift through this, get a gut feeling for what we need to do on some of this stuff. The way I would kind of look at this is you could have a situation, they almost introduce this thing called a parallel plate capacitor. They introduce it before they do more of a definition of what's going on there. Let's hit some of the highlights of what's going on with some of this stuff and take it from there. I'm looking at topic 16, at least initially, on pages 558 through 560. 558 through 559. Let's talk about this idea of electric potential energy and electric potential. They're closely related. In a sense, there's somewhat easy ways to talk about this, I hope. And let's see how we're going to do it. Let me stay low, wait for this to dry a little bit. We have said a number of things. Now, those of you, this is a non-calc version. This book has non-calculus treatment. They brilliantly handle in a non-calculus way much of electricity and magnetism. Let's just briefly, and you'll see it in the solutions that I have, where I opt into a little bit of calculus, because there are some students in the non-calculus courses that have had calculus. So for your personal enrichment, it's good to look at it. You don't have to know what I'm about to do, but just kind of see some of what we said. At least kind of see what we said earlier. Remember, we talked about, if there's a huge positive charge conglomeration, and you've got a negative charge here, and this thing's hammered into the universe, it ain't going to move, and you're here at a distance, R1 from each other, and you physically pick this thing up, and you go very far away, and you go here, Well, you went from R1 to R2. You had to put energy into that. We said this last time. I simply just said it, didn't write it down. So it's the same thing that I said last time. The fact that this is, let's say this is not going to move. Let's do some thought experiments. Somehow this thing's hammered into the universe. It's not going to move. And only the negative, the negative charge is going to be separated from it. Well, there's an attractive force there. You're going to fight the whole way to do that. When you do that, you have to do work to do it. What kind of work? It's positive work. This positive and negative means nothing. Let me just get a magnitude here. Make sure it's a positive amount of work I've done. What did I do there? Well, what I did right there is I put work into this system, and I gave the system potential energy. I increased its potential energy. What does that mean? That means if I let it go, if I'm holding on to this charge that wants to go right back, if I let it go, it's going to increase its kinetic energy as its potential energy is decreasing. Its potential energy decreases as it goes to the left, and the kinetic energy increases. If this thing was moving really fast, well, it's going to slow down until it's brought to a dead stop. And then if you let it go, it's going to have the exact same magnitude velocity in different places, starting out with very slow velocity, just like I had slow velocity to get here. It had slow magnitude velocity to get to this point. It had a lot of it right here, and all of it was all the kinetic energy was being taken away. When you set up those, mechanical energy equations from Newtonian physics, you might say, well, look, I'm not going to worry about friction. I'm not going to worry about a whole lot of other stuff going on here. I'm just going to say potential energy initially present plus kinetic energy initially present, at the end of the day, is going to equal potential energy finally present plus kinetic energy finally present. You're looking at something like, you could say there's, back in the day when we were doing this stuff, we could be talking about a spring. We could be talking about a gravitational situation that this thing is climbing a hill, or there's a spring or a rubber band or something like that, or something climbing a hill, or all of the above. Well, let's make it easy. Let's just say we're dealing with mgh, how I could say it. Let's say mgh1, that's the initial. This is 1/2 m v1 squared. This is mgh2. This is 1/2 m v2 squared. If you subtract this stuff, if you subtract this amount, the 1/2 m v1 squared, if you subtract that on each side and subtract mgh2 on each side, you got mgh1, mgh2, mgh1, mgh2, 1/2 mv2 squared minus 1/2 mv1 squared. Here's a 2, here's a 1, here's a 1, here's a 2. That's kind of the motivation for a lot of times where they throw a negative number in there. They throw a negative number in there, throw a negative sign in there. They're opposite, there's some sort of opposition in sign here according to the bookkeeping that's going on. I don't want to go into that too much. I tried to do that at one point at various times when I've lectured in the past and in the recent past, and it was kind of, it can get probably more confusing for everybody involved. So whatever. But the big thing to know here is, here there's essentially, the one, the I, the 1 pertains to the I, the 2 pertains to the F. Here's an I, here's an F. Yeah, I know, but here's the F, and here's the I, if you want to go there like that. One or the other is going to work on that. It doesn't really matter. As long as you just know that, H1 is HI, H2 is HF, V1 is VI, V2 is VF, whatever. I mean, we can play a whole alphabet soup here, guys. The big thing is there is some interesting stuff going on here. In general, in terms of absolute values, and this is what I was trying to discuss at various points when I've discussed this in the past, sometimes not very effectively. Have this in your mind. Have this in your mind that essentially, the absolute value of the change in potential energy and the absolute value of the change in kinetic energy are equal to each other. A lot of times you can just kind of like throw these symbols out the window and say, look, let's just get this straight. I can somehow figure out a difference in potential energy. I can somehow figure out a difference in kinetic energy, and the magnitude, which is a positive number, or 0, but not less than that, the magnitude, which is greater than or equal to 0, the magnitude in the change in potential energy equals the magnitude in the change in kinetic energy, and it just makes the whole matter a lot easier. I had a student, I've had students talk to me in the past and say, yeah, as long as we're aware of, what direction things are going. I say, yeah, absolutely, you've got it right. Because these negatives, the way they're written, could really be a recipe for disaster if you're not careful. Not that there's anything wrong with them, but the major argument here, more than anything, is the bookkeeping. When I was over here, if this thing's flying really fast, wow, that real fast kinetic energy, that great kinetic energy is being dissipated, not dissipated, being converted, I guess you say, to potential energy. It goes to 0. 0 kinetic energy, it's all potential energy. You let it go, it's a mirror image just going the other direction. If it was going 500 meters per second right here, going that way, right here as well, if it's going 500 meters per second right here, then it's also going 500 meters per second that way. If it's going 1,000 right here that way, it's going 1,000 right here when it comes close to here. If it started going at 20,000 meters per second that way, at the end, on the way back, 20,000 meters per second. The big thing is get an idea what is what. Well, who's pulling? What is pulling what? If I know there's a pull going on and I'm going against the pull, or I know there's a push going on, if I'm going against the push and going closer, I'm increasing potential energy. If I'm going away, I'm decreasing potential energy. If it's two positive charges, there's a push going on, I'm going toward the big positive charge, I'm increasing potential energy. My kinetic energy is going to drop as I'm going toward it. If there's a positive and a negative, that same thing happens, but you got to go away for that to happen. I mean, your kinetic energy is getting bigger if you're a negative charge going to a positive charge. Your kinetic energy is getting bigger the closer you go. Your potential energy is getting smaller. But your potential energy will get bigger if you're the negative charge running away from the positive charge. Greater potential energy, but less kinetic energy. It's the only thing. That's what I was trying to say last time. They sort of put the carriage in front of the horse on some of this stuff, you guys, when they do this. So let me let's kind of talk about it a little bit. They kind of introduce the and again, guys, the board it's got its moments here, guys. It's a little bit on the slippery side when I'm trying to write this stuff, but luckily the chalk's holding up pretty good, so I think we're going to be okay. Let's keep moving. So I guess what I have is, let me see here, guys. Okay, I'll look a little bit. Okay. So they're kind of they do some stuff here, guys, and so let's go with them, and we'll talk as we need to talk, I guess you could say. They put a plate, and they're not. I don't think this is meant as any kind of great artistic accomplishment on their part, and certainly not on my part. But they're saying there's a whole bunch of positive charges there in aggregate, and there's a whole bunch of negative charges on this one in aggregate. And they're saying essentially kind of the same way we did earlier, and you're going to see this when you look at my work in the other films that have the problems from chapters 15 and chapters 16. In other words, from topics 15 and topic 16. And I go into that and say, well, wait a minute. The E field is constant throughout, so it's going to make our life a little bit easier. And then they start throwing some stuff in here, guys, that can maybe make it challenging. But there's an E field, an E field, an E field. It's the same in all circumstances. And it's just saying there's a high the closer you are to this thing, the higher your potential energy. And the closer you are to this thing, the lower your potential energy. This guy wants to expel you and bring you over to here. If you start right about on the surface or close to the surface and end up getting over here to this surface, there's work that gets done. You're getting pushed. They always use as a test charge. Typically, they regard the test charge, a very small charge necessarily, or just some kind of test charge Q, is associated with some kind of positive charge, a positive test charge. How would a positive charge behave in a certain circumstance? Well, we know what a positive charge would do in this circumstance. If it's right here, well, you tell me, what's positive and positive in proximity to each other? Let's assume the bars here, let's assume the plates here don't move. They're hammered in somewhere. Well, if there's a positive charge next to a positive charge conglomeration, that positive charge gets expelled from there. You know what these negative charges do? They want to accept it. So the E field goes, the direction of an E field is always the direction in which a positive charge would move. In what direction would these are drawn in reference to a positive charge. If there's a positive charge here, right next to this, it is being expelled by those and attracted by those, and man, it's just going that way. Therefore, the E field goes in the direction that I just showed you. If it was a negatively charged particle, here, it's being expelled from the negative, being drawn to, it's going that way. Man, that's true as well. But that's not the definition of E field. E field is how does a positive test charge behave? That's the direction of the E field. Okay. So, with that in mind, there's a lot of potential energy up close, but there ain't a lot of potential energy. There's a lot of potential energy right here when you're at the positive stuff, but when you get over to here, and these are a distance D apart, surface to surface. Distance D, I don't know, the book calls it something different. I'll call it D. I don't know, we could say a lot of stuff. We could say, the book sometimes calls that distance D delta X. D and delta X are synonymous. You're going to see some stuff like this. You see things in different literature, and at least in my notes sometimes you see it as well. There is going to be a loss of potential energy. There's going to be a loss of potential energy. The book's got some negatives flying all over the place. I've tried to handle that kind of stuff in the past, and sometimes it is, it's to me somewhat, through no fault of the authors who write a brilliant book, it can kind of be a disastrous thing to try to explain sometimes. So let's kind of opt out of this thing and just say, I'll tell you what. There's a change in potential energy that is going to occur. There is going to be a loss in potential. Well, that's an interesting point in its own right. If I have, let's talk about that. Let's do contrary, a little bit contrary to what the book is doing. Not too much. The book's doing essentially the same thing I'm doing, but they're not maybe explicitly saying this. Why don't you put a positive test charge right here where my hand is? a positive test charge, man, that guy doesn't want to go anywhere. There's a negatively charged situation here. The negative is attracting the positive. You ain't getting out of there. In fact, the only way you're getting out of there is with work. What does that mean? Well, if I got a positive test charge right here, it's attracted to the negatively charged particles, and it is being repelled by the positively charged particles. The positive particles are saying to the positively charged particles are saying to the positively charged particle, we are pushing you, we want you to stay there. And the negatively charged particles are saying, we are attracting you and we want you to go in the same direction in which you're being pushed by the positively charged particles. You put a positively charged particle right here, it ain't going anywhere unless you do work on it. If you got to pick it up and push it all the way to here. How much work did you do? Well, how much work did you do? If you had that I'm going the other direction now. I had to do a force, electrostatic force times distance d. That's the work. The electrostatic force times the distance d is, well, didn't we say a while back, you guys, that E was equal to Fe over Q. Q is the positive test charge. Multiply by Q on each side. Multiply by Q on each side. You got this. Fe is QE. We've been there. We've already done that. Times D, or times delta X. The D and the delta X are the same. The book's got a little different scenario. The book put a negative on there, and I'll explain that in a second. For our purposes, the work that you had to do is QED. Wow. You did all that work to go from here to our right for this positive test charge to go to the left. What did you just do? You took it from low potential energy to high potential energy. You gave it, it gained this much potential energy. It's the change in potential energy. What would be the change in potential energy once you're here and you let the thing go? It would lose that much potential. I'm not going to do what the book does. I've tried in the past and it was, in my judgment, not great. You're going to lose this much. Where's it going to go? Into kinetic energy. That thing's going to be going fast. If this thing was going really fast right here, going that way, it's going to lose all that kinetic energy and have all potential energy. If you let it here go where it has no kinetic energy, it's going to lose all the potential energy, but right before it hits that plate, it's going really fast. And that's some of the stuff we talked about last time. Well, you know, this is kind of where things can kind of go south if you're not careful. You look at this, this was essentially what we're talking about regarding potential energy. So, potential energy equal to all that. Now, what they try to do, they kind of give a big picture here. Let me try not to. Let me see a bunch of things. I mean, and I do mention this in the other films. I don't want to repeat. I think you've got more than enough to do with all the other films that I gave to you if you want to look at them. There's a lot to look at. You don't have to. You can look at my PDFs if you wish. The PDFs are in there as well. In some of these films, I do have PDFs in there as well. Of all the stuff, and then you can also look at the PDFs based on what I've given to you. The big thing here is there's a change in potential energy, you guys. This change in potential energy don't know where I want to go on this now. The change in potential energy divided by the positive test charge, and let's kind of just a little bit of a time out here for a second. If you want to say the change in potential energy divided by a positive test charge is the work that you had to do divided by Q. We're going to come back to this at some point, not too far down the road. And if you take if work is QED and divide by Q, you got E field times the distance, E times D. So this is kind of a special case scenario. This thing right here and this thing right here, they call that delta V. V for voltage, I think, but we'll just call it delta V. That's the potential. That is the potential difference, the difference in potential. So this right here, you guys, when you're doing this, and they say it again. I'm not crazy about these negative symbols all over the place. So I'm not gonna go there. Is what I'm not gonna do. This is essentially, guys, and this is to help you, and I hope it does. The work you did per unit charge, work done per unit charge, is called the potential difference, delta V. If you multiply by Q on each side, the work that you had to do was Q times delta V. But delta V, well, what is delta PE? Isn't that joules? What is Q? Isn't that coulombs? Joules per coulomb are the units of potential difference, of potential. If you multiply potential difference by coulombs, you get joules. This is, this right here is joules. This is coulombs. It's work per it's work per unit charge. It's kind of, you can kind of see there's a similarity here, guys. Do you remember how we said, we said a lot. I mean, we said FG was M times G. We said FE was Q times E. Now that we're talking about work, we're talking about Q times delta V, or just, and that's potential difference. You went from a high potential to a low potential. Potential high, so in other words, the work I had to do here was I went from a high potential, and actually in this case it was a low potential, and I went to a high potential. So I took H for high, L for low. The change in the two was the delta V that we're talking about. Now, be aware, I think I've seen this in other books. I've kind of stayed faithful to those other books, for better or worse, I guess. So be aware of both scenarios. Oftentimes, what they mean, and I think Serway and V will do a better job than this, but the delta V and the V are synonymous depending upon the book. A lot of times they'll say, well, yeah, I'll just, if I take VH minus VL, I'm going to call that V. That's the potential difference. The best way to write it is that it's delta V. But Serway and VU will do a really good job on this. And that's technically the way you want to look at it. Frequently, you'll see it written like this. So it would not be uncommon to see something. If the V is synonymous with the delta V, you'd write it like that. Be aware. They mean the same thing within a particular content, within a particular context, depending on the context, depending on the textbook. Okay, so just be aware of that, you guys. It's some fascinating stuff. I mean, how they actually get down to something like that, you guys, and how to look at it. Like, you know, the electric potential, how that plays out. Well, I mean, by saying something like this, there's some interesting stuff we could talk about and should talk about, in fact. So let's see what we got here on this stuff, guys. Kind of go around full circle in a sense. So we're looking at this. We've got this situation. Don't know that I'm going to keep needing this, but perhaps I do. And it could be a lot of stuff. It could also be from a distance that you're talking about. You could have a delta R rather than a delta X. Delta X equals delta R equals D. There's a lot of ways you can write this, but let's talk a little bit. Now, I've done what I'm about to show you guys. I've done it in classes where obviously there's a calc version, there's a calculus treatment pertaining to these physical realities. We can do a calculus treatment of it. Obviously, the course for which I am speaking right now in this video is a non-calc version, but I show it sometimes, and you can throw it out the window. You don't have to use it. If you have the calculus background, it's there for your personal enrichment. If you don't, just know what the conclusion is. And we did that last time. Let me just quickly kind of tell you, I mean, how the basic argument of this stuff proceeds. So you can kind of look at it and say, well, okay, you know, in general, when you're talking about now this is kind of a different phenomenon here. In this case, in the parallel plate capacitor that's here, we don't even know what a parallel plate capacitor is just yet, but we know that, well, okay, they kind of put the carriage in front of the horse on this one. They kind of showed us this. In this case, E was a constant over here. In this case, E was equal to a constant, and I was able to do the song and dance that I wanted to do, and that's fine. Those present recently, when I tried to talk about this, some of this went well. Most of it, in my judgment, did not, and that's my fault. That's completely my fault. Some time ago, people that were there in person when I tried to discuss some of this last time. Let's say you're talking about, you know, and we're not going to dwell on this greatly, but we already kind of mentioned this. Let's kind of mention it again. Let's say you've got, you know, let's say you got a situation where you've got a positive conglomeration of charge, and you've got a whole lot of ways to proceed with this, guys. As long as we know where we're going, let's see what we can do. If I got this thing to be negative, and here we go again, if the distance between them is R1 right now, and I'm going to increase the distance to R2, further away, okay, we've done this. I mean, as this is done, you're going to have to put positive work into this to increase the potential energy. And this is associated with this great equation that we were able to derive using Gauss's law and see experimentally when we do a lot of stuff. This is, you know, let's say this guy is big Q, this one is little q, and I'm not worried about the signs, guys. I know that if I'm taking a walk to your right, and there's a positive and negative there, I better put a lot of energy into this thing. This negative and positive stuff is not a big deal for me. Let me be aware of the magnitudes. Let me find out what goes on. And let's say you got this. K is a constant, capital Q is a constant, and lowercase q is a constant. R squared is not. We also know that the work that you're going to do is going to be the change in the potential energy, and we already know we already kind of set it up to be positive. Now we're just going to have to be careful about this. It's going to be Fe. This is constantly varying phenomenon, guys. The further away that you're going, wherever you're going, actually, different from where you started, is a variable quantity. That R on the bottom doesn't remain the same. It's constantly changing. It's variable. It ain't going to be the way it was here, where I could do the simple multiplication, and it was pretty easy stuff to actually figure out what I was getting there when I got the QED, right? The QE delta X or the QED to get the change in the potential energy. It's a different dynamic. Now, we're not going to go greatly into this. I've already done this before in the past, so I don't want to drive us too crazy with it, but let's just write it down there, have it written on there, and we'll see how we'll proceed. I'm going to integrate this thing from R1 to R2, and I'm probably going to manipulate this integral even after I do the integral. You'll see what I'm doing in a second. I'm going to go FE times dr. I'm changing r and I'm going that way. It's increasing. That's going to be this situation. I just don't want to do too much of this, guys, because it's not really directly relevant to our class, but like for those that have the background here, the K, capital Q, and small q are all constants. So you're going here, if they're all constants, bring them out. They ain't gonna, that's not going to change anything. In fact, I'll call them, even maybe the negative gets me off the hook. If that's positive, that's negative. That's a positive times negative is a negative answer. Fortuitously, it's going to give me the right positive answer. Why is it a positive answer again? Beyond any sort of formality in the labeling pertaining to the mathematics, let's at least get magnitudes strongly under control and know what the answer is. Well, the answer, I don't know what it is. I got to do the mathematics to get an answer, but I do know this much. It's not a negative answer. If this thing is being drawn that way, forever you got to fight that way, you're going to have to do positive work to get an answer. You better get a positive answer here. If you don't get a positive answer, get one. Just put positive, the actual answer at the end of it is going to be just fine. So you're actually doing this, and you're almost tempted not even to put the R1, R2 in there, but let's put it in there. We got this, and it's quite a song and dance. And I've done it before, guys, so forgive me. Those that were with me in the lecture, you're going to see it. You actually do the thing at the end of it. You got negative 1 over r. R2 is a big distance. R1 is a small distance. This thing is, now I'm going to, for our purposes right now, I don't care. I know that capital Q and small q and k are all constants. For my purposes, I'm going to say what's their magnitude and I'm going to treat everybody like positive. And at the end, I know I need a positive answer. So if I don't get a positive answer, I'm just going to get the absolute value. But I know I am getting the right magnitude here. My argument is sound. That's the big thing. Know where you want to go in the big picture. Know where you want to go in terms of the directions. If I'm going to the right, I'm putting in a positive amount of work to get to where I'm going. All right. You actually do this. You evaluate between the two. I don't want to beat this thing completely to death, but we've got this right here minus a minus this right here. And again, if there's just positive numbers here, K, Q, Q, let me just see. I think we might luck out on this one. Minus a minus is this. R1 was well, that's a good question. Make R1 a very small distance. Make R2 a very big distance. What's 1 divided by very small? Big answer. What's 1 divided by very big? Small answer. Big answer minus small answer. Big answer, big positive answer. Big positive answer minus small positive answer is a big positive answer. I said these are positive. You're done. If you were to take this guy and move him all the way to infinity, how much work do you have to do to go to infinity? Somebody might say to you, I don't want to say, I'm not going to say, I don't want to say, I could say, speaking for myself, I could say foolishly, oh, I'm going to an infinite distance. It's got to be an infinite amount of work. Well, wait a minute. Why don't you set this thing up as the R1 starts somewhere. The R2 goes to infinity. R2 gets bigger and bigger and bigger. This is the answer. End of the story for the goalposts here. Let's make R2 infinitely big. If this is really, really huge, 1 over something very big is close to 0. 1 over something even bigger than that very, very big thing is something even closer to 0. In the limit, as you take it toward infinity, it's practically 0. If it's practically 0, the potential, the amount of work you got to do, let's call R1, let's call it R. Now let's call it, that's a constant now. I'm not doing integration anymore. Let's call it R. That guy right there, if you take it to infinity, that is the magnitude. That is the work. Notice, it's a finite number, my friends. It's a finite, you're going an infinite distance away. The answer would be going toward infinity if the force remained non-zero, positive, and constant. If the force was constant, for you to go to infinity would be an infinite amount of work that you'd have to do. But the force is inversely proportional to the square of the distance. The force keeps getting smaller and smaller and smaller. And in the limit of these summations, I guess you could say, the limit goes to a finite quantity. It goes to this. And that's pretty significant. That's pretty significant. And that's the PE. That's the PE in terms of the delta PE. Now, if you want to call it, well, here we go. Let me just put the carriage in front of the horse again. Let's do this. Delta V is delta PE over Q is KQ, small q, over R. I ran out of room, guys. Divided by Q. So let me get rid of some of this, guys. I'd like to not get rid of any of it, to be honest with you, but let me get rid of some of it. Take it to infinity, and that's really their definition in that thing. The positives and negatives are potentially one hell of a mess. So take yourself out of it. Take yourself out of that situation. And just say, hey, look, here's what he got. And when he got this right here, all of that is where we're talking. I mean, you're getting to here. And right? So the delta V sometimes called V, just be careful, because I do that in the problem solving. I go one and the other on this thing, so watch out. The delta V, as we said, was delta PE over Q, which was the delta PE, the work that we had to do to go to infinity, which was a finite answer. If the force was not variable and it was a number greater than 0, if the force is not variable and is a number greater than 0 and is a constant, means the force isn't variable. Force is not variable means the force is a constant, and if it's greater than 0, the more you go, the more energy you need to put into the system. To go to infinity, you need an infinite amount of work. But not when the force is variable, my friends, according to this. Hence the need for calculus in there. You don't have to go in there, but I just want to tell you, this thing kept getting smaller. That guy kept getting smaller because of that. It's a different dynamic. So you look at it, you got what you got here, guys, and you say, okay, well, what did he say? Delta P, that's the work. And then I'll say to you, yeah, please kind of talk. Delta V is delta PE over Q is work over Q. Kind of going backwards here. We already said that a while ago, right over here, way in the corner, you guys. And we're just taking it. We're going. And get this thing to work. And you're looking at it. You got all this, and like I said, we're looking at it. So I mean, it's everything I wrote here. At the end of the day, it's coming out to here. It's coming out that delta V is indeed going to be KQ, the big charge conglomeration. The Q's, the small Q's cancel. And they got a graph on this in the book and how this relates. What does this tell you? Well, the further away you are from big Q, the further away you are, the less potential difference there is. What does that mean? Well, that means the further away you are, if I started this walk from R1, if R1 happened to start 1,000 miles that way, let's say R1, this is like, let's pretend there's no other forces in the universe for this problem, just to visualize it. If this is 100 miles away from this guy, that's pretty far. Well, let's say it's one. I don't know. Let's actually say, let's say it's 1 meter away. And get your answer. Well, I'll tell you what. No, I'd like to start this guy not 1 meter away like I did here. I'd like to start it 1,000,000 meters away that way. Well, at such a big number, I don't need that much energy at that starting point to get it all the way to infinity. So the delta V is a smaller number. And here's how it relates. And it's an interesting, it's a hyperbola. You draw this thing, it looks just like 1 over x. Y equals 1 over x. Has that definite look, and they have that in the book as well. So, I mean, it's rather interesting how they're going to talk about some of this stuff, you guys, and we got it, and I'm making it look like this. And this is in coulombs. This is in coulombs. This is in joules per coulomb. 1 joule per coulomb is called a volt. There's your volt. There's that famous volt. A joule of work per 1 coulomb is 1 volt. The delta V, 1 joule per coulomb, 1 volt, times this many coulombs will tell you how much work it is that you need to do. That can be done across that potential difference, delta V. Sometimes rather than delta V, you see, I've seen books, it's been a while, guys, but my memory's not great on this. They use just V sometimes. You just got to be careful. I also use V when I talk about it. Delta V, when push comes to shove, is probably the better way to do it. But you can see it in the literature. You can see it in my own solutions. I have a V in there rather than delta V oftentimes. So just watch it. Some other stuff to say. Kind of doing some stuff here, guys. I'm leaving a lot up here. It's a good question how much you want to leave up here. Somebody's going to come back. Some of this maybe needs to be erased, but let me at least leave some of it up there and we'll take it from there. Let me kind of leave that as well. Well, that could probably easily go as well. Okay. We can also, a number of things to be said here, guys, so let's try to make some sense. They said, okay, if you wanted to talk about the work required to do something, we said if you had, if we're talking about work equals, this is more of a formality than anything, I guess you could say. This is not a lot of work if we talk about an electron or something with the charge that an electron has. If the work required if you were going to do all this work on a charge that had 1.6 times 10 to the 19th coulombs, and you did it over 1 joule, you did it over associated with a potential difference of 1 joule per 1 coulomb. That's the same as this is just a definition of some terminology in unit that I think is good for you to know. Negative 1.6 times 10 to the negative 19th coulombs times 1 joule per coulomb is called 1 volt. This would be 1.6 times 10 to the negative 19 joules. That's the work you would have to do on a very tiny charge to get it across a potential difference. How much kinetic energy does it? Now look, the potential, I could be talking about a charge being fired this way. Well, how much kinetic energy did it acquire? The same amount of, how much kinetic energy did it acquire? It acquired the same amount of kinetic energy as the potential energy that it lost. If it was here and you move it up this way, how much potential energy did you give it? Well, that'd be about the same amount as the kinetic energy that was lost if this thing was going really fast right here for some reason, and then it just gets brought to nothing here. How much kinetic energy did it lose as you're fighting to go this way? Or how much potential energy, how much kinetic energy did it lose, which is the same as how much potential energy it gained. How much potential energy is lost going back? It's the same amount as the kinetic energy that's gained. Again, as a student of mine, as numerous students of mine have brought up in the past, it's where the instincts are on this stuff. So this is the work that you would do. They call this right here, that amount right there, they call 1 EV. 1 electron volt. 1 electron volt is a unit of energy that's equal to the amount of energy required to, the amount of energy that is acquired, depending on what's going on, when something with a charge of 1 electron is experiencing 1 volt of potential difference. How much kinetic energy is acquired? Ooh, that's how much potential energy is lost. How much potential energy is acquired? That's as much as kinetic. That's as much as the kinetic energy is lost. Doesn't matter. How much work would it take in a so-called easy way to look at it? Hey, let me go from low potential to high potential. How much work do I got to put into it? Well, for me to move that electron through a potential difference of 1 volt, I need 1.6 times 10 to the negative 19 joules, which is the same as 1 electron volt. Which is what they call, by definition, they call that 1 electron volt. Okay? So that's the thing, guys. Well, I mean, I guess there was a good reason I left this thing up here. At some point I'm going to have to alter it a little bit, but this right here, let's say it's connected to something, and it's connected to some battery, and the battery charges this thing up with, charges this thing up with, we always assume it's positive charge. We know electrons are the thing that move. But for our purposes, we're going to say, you know what? Let's pretend there's these imaginary particles that are positively charged, just like electrons, and those are the things that do the moving. They developed all their argumentation with positive charges. What happens with a positive test charge? What happens with positive test charges? I know negatively charged particles called electrons are really what generate the electricity. Well, these imaginary positively charged particles move in the exact opposite direction, but they solve all the same mathematics. So you want to kind of keep an eye on that when you're doing that. Somehow you have a battery that took away all the positive charges from here and distributed many positive charges over here. So there's a negative amount of charge here. There's a real big absence of positive charge here. In aggregate, it's negatively charged. And here, there is a positively charged abundance between the two. And we got the E field that we got. We got to talk. We're going to assume that there's an amount negative Q of charge here and an amount positive Q of charge here. After the battery was connected, and after that they disconnected the battery, and now the chargers can't go anywhere for our purposes. They define, and again, this is where I get into the different ways you can kind of look at what some of this stuff is. So let's talk. Okay. Well, they got this thing called capacitance. Capacitance is defined. They put those three symbols there, meaning this is by definition. They say capacitance C, you pick, these are symmetric. One's very, very negative, and one's very, very much an absence of positive charge. You are in a deficit of positive charge by Q. You're in the negative range. You're at negative Q. That's how far below you are to this being neutral. You're this far below from this being neutral, and here you're this far above from this being neutral. The magnitude is Q. There's positive Q, there's negative Q. You only take one of them. Take one of the plates and say, what's the magnitude of the charge that's on there? They're symmetrically associated. Capacitors. Topic 16, page 558. A capacitor consists of two metal plates with charges that are equal in magnitude but opposite in sign. The capacitance C of any capacitor is the ratio of the magnitude of the charge Q on either plate to the magnitude of potential difference between them. Let's make the long story short. The magnitude of the charge on either plate divided by the magnitude of the potential difference between the two charges. If you somehow connected a wire here and a wire here, and if you had them on there, and you brought the wire down here, and you connected the wire, we're going to say only positive charges flow. All these positive charges would flow over to here until you had two neutral plates. And work would be done. Why? Because charges are moving within that wire. We're not worried about resistance or anything like that right now. We're just saying there'd be something going on that way. Frequently, I don't want to beat this thing up completely. I said in some books that capital V is the same as the delta V. Let's use their argument, the way the book is going. Sometimes I go the other way. I've already told you that as well, so watch out. The V and the delta V mean the same thing. You better watch out with the context for where it could occur. So they're saying this. They're trying to say, given this right here, for this parallel plate capacitor, are you able to tell me what the charge would be? Well, there's a lot you can say on this stuff, and like I said, I work with this I guess we got to be pretty flexible. We can see either way as long as you know how to go back and forth. The person's name might be Joe or it might be Joey. It might be Jim, it might be James. Might be Jim, might be Jimmy, might be a lot of things. So how you actually are going to identify what a person's name is, how you actually label a person, how they want to be labeled regarding some of this stuff. So how are you going to do it? I'm kind of looking right now, guys, to kind of see how I'd want to look at some of the stuff that goes on here with this stuff. I'm really tempted to look at these a couple different ways. We said that for all of this charge, I mean, there's a way you can get the charge to go all the way around, guys. You could connect it with a wire this way, or if you could somehow just have it come right across to here. Okay. I want to get into all the specifics of that. We just got to know this is what we're looking at. Can we draw a conclusion from here? For some reason, there's a number of ways that can be proved. Let's go where that is, and I'll kind of mention something else. I might put the carriage in front of the horse on some of this stuff, guys, or at least go a little different order than what the book is doing when they're doing some of this stuff. So let's see what we got here. They basically, it kind of gets you out of the woods with this a little bit. If you want to look at it, they're saying, wait a minute, can we talk a little bit? Well, C is equal to Q over delta V. Isn't sigma Q per area, charge per unit area? So Q would be sigma times A. Sigma times A. Delta V, now we said this last time, you guys, delta V, didn't we, how sharp are we on this stuff? Didn't we do that problem early on where we said that W was QED, delta V was W over Q, was QED over Q, delta V was ED. Okay. How sharp are we? Do you remember the problem that we did together? Actually did it in class some time ago. We said that, let me see here. They say something, and let me say it too. They did say something. So let me see here, guys. They wrote sigma over epsilon naught. I think the answer that I gave somewhere else was something different. Very, very close to that. Remember when we talked about, we were using Gauss's law in chapter 15. Let's just, because I think there's a subtle point here that I perhaps am missing. Just find it. Right. Okay, yeah, there is kind of a subtle point here. If we look at, and for those of you who have the book, and if we look at topic 15, page 519, we get an answer of sigma over 2 epsilon naught for the E field, but that's for an E field. That's for an E field associated with one plate. The other plate right above it, or right next to it, is also contributing an E field, which is also sigma over 2E. The positive test charge is being pushed by the positively charged. The positively charged plate pushes the charge, the positive test charge, and the negatively charged plate helps in that push by pulling the positively charged test charge. The E field associated with each one of those plates is sigma over 2 epsilon. Sigma over 2 epsilon naught. So together, and they say it on page 519 really, really well. An important circuit element that we studied extensively in the next topic is the parallel plate capacitor. The device consists of a plate, a positive charge. I just think that's more than I need to say right now. The big thing is this. We found, the real big thing was when we solved that example problem we had done together, and it's in the Serway book on pages 518 and 519, the E field is 1 over 2 epsilon, is sigma. E is sigma over 2 epsilon naught. Now what happens is one of the chart, for one of the plates, it's magnitude sigma over 2 epsilon naught. The other, so the E field, if you just extinguish this right now and just look at this, you put something here, the E field is the same everywhere at any height. We've talked about that. I give a pretty good, I hope I give a pretty good derivation of it. Some of it involves calculus, but you don't have to. Okay, but I gave you a whole bunch of different looks on that on a particular film. Right here, there's an E field associated with what's happening right here. That E field associated with what's happening right here, that E field is sigma over 2 epsilon naught. The E field is, for our purposes, a push to the right. A positively charged test particle is being pushed to the right, associated with an E of sigma over 2 epsilon naught. That same positively charged test particle is being pulled with the same E field magnitude, helping out the other one. Look, I'm going to make a long story short. In totality, it's this, the positively charged particle, the positively charged particles associated with one plate, and the negatively charged particles associated with the other. And for the life of me, I just cannot draw a sigma, guys. You add these together, is sigma over epsilon naught. What's going on here? That's E in totality. E is sigma over 2 epsilon naught for one of the plates. The two plates work together, so you're adding them together. And you get this. This is D. The sigmas cancel. The sigmas cancel. Epsilon area, this is the area of one plate. This is the area of one, and the plates are symmetric. The plates have identical areas. One plate has area A, the other plate has area A. In total, the area is 2A if you add the two areas. I don't care about that. I'm just looking for one plate in the definition. So it's this. And the sigmas cancel, the sigmas cancel, the epsilon naught goes over here. I was tempted to jump a little bit off schedule on this. I think it'd be a little easier if we look at something else I wanted to kind of say if I could. Okay, great point here, guys. All right. So we got that. And try to think here, guys, how do you want to look at something like this? There is, again, a number of ways to go on this. I'll try to get this and try to bring it to an end here, guys. I'm trying to not talk incredibly much on this. I do want to say this much. There is, let me get to, so we can kind of get it out of the way a little bit and talk about it. Page 552, 553. Let's just get a kind of a brief gut feeling as to what's going on here. Capacitors with dielectrics. So let's take a look. Capacitors with dielectrics. A dielectric is an insulating material such as rubber, plastic, or wax paper. When a dielectric is inserted between the plates of a capacitor, the capacitance increases. If the dielectric completely fills the space between the plates, the capacitance is multiplied by the factor kappa, called the dielectric constant. The following experiment illustrates the effect of a dielectric in a capacitor. Consider a parallel plate capacitor of charge Q0 and capacitance C0 in the absence of a dielectric. The potential difference across the plates is this: because the capacitor isn't connected to an external circuit, there's no pathway for the charge to go. If you put something between them, the voltage, the tendency for the charges to want to flow to one side of the plate to the other side of the plate will go down. So what happens is, let me do this so we can actually kind of talk a little bit more. Say you try to see what I'm going to say here, guys. Okay, we got this. Remember this, and we'll have use for it in a little bit, I guess you could say. They are saying, I'll just leave this up here a little bit too. There's a whole lot we're leaving up here. If you were to put a dielectric material that does not, it is something that is not a conductor by definition. It's going to hamper, if you put it between the two plates, you're going to hamper any possibility, well, you're going to hamper to some regard, in some sense, the tendency for the, if you could somehow draw a connection between these two, there's a tendency of there to want to be a flow between the two. In other words, there want to be, if somehow you set up the pathways, we could get the positive charges to come over here. True. There's a voltage. There is a E field, and there is a voltage. There is an anthropomorphic quality, if you'll allow me to say that. There is a need, there's a want, I guess, for the positive charges to get over here. There's less of that want if you put a dielectric material between the two. There's not as much potential difference between the two plates. And that's kind of where their argument goes with that. And they say basically, you'd used to have, at some point, let me leave that there for now, guys. You used to have, let's say, delta V, there's an amount Q0. And let's say, before you had a dielectric present, you had, let's say there was you got Q0 over, they got, let me see how they write it. They go delta V0. Sometimes I write V0. Guys, I already told you, be warned. We may start writing it like this a little bit sometimes for convenience. It just tends to go a little faster. Maybe that's why they did that in other books. Maybe that's why they do that in other textbooks, you guys. But you're looking at a situation, let's say you have an initial situation looking like this. That's very similar to everything we've been talking about. And there's no dielectric present. Well, if there's no dielectric present, the way they play the game is they say, okay, well, let's multiply by dV0 on each side and divide by C0. dV0 and divide by C0. Okay, no big deal. I just manipulating something right there. No substantial change to the mathematics. I'm just writing it in a different manner. Then they're saying here, guys, if you want, you can say that basically what's going on is if you put a dielectric of dielectric constant kappa, your potential difference between the two plates, and that's a kappa, like a K, Greek letter kappa, and forgive me. This was what the potential difference was. It was a big potential difference initially, and then you filled it with dielectric in one way or another. You somehow filled it. You obstructed what would be an easy path, potentially an easy path for charges to flow. When you fill it like this, there's just not as much potential difference. There's not as much tendency for this thing to want to go. How much less tendency? Well, this is what it used to be, and now it's kappa on the bottom. Delta V0 divided by kappa is what that is. If that's the case, then you're not looking at this anymore. You're looking at a new which is going to be equal to, well, Q0 didn't change, my friends. But the delta V is this guy. Q0 didn't change. The delta V is delta V0 over kappa equals Q0 over delta V0 times kappa. Whoa. That looks awfully familiar. That was the original. C, this is what you had originally. The capacitance here is different. It's the same thing you had here, Q0 over delta V0, same thing. That was C0, but kappa for the C. C equals kappa Q0 over delta V0. C0 is Q0 over delta V0. The new capacitance is a factor kappa what the original capacitance was. And they're saying what would happen. This had no dielectric in it. If you want to put it as a dielectric, it was really C0 equals epsilon naught A over D. You put a dielectric in it, it's going to look like this. For that same thing, I say, hey man, it's the same thing you had. It sure is. Just be careful. When there's a dielectric present, you put a kappa. And they write it. The book writes it a little differently than I just did. That's the way. Let me just kind of go consistent with the book. I don't know if I want to go consistent with the book, to be honest with you. But you got this right here. That's the answer. That's fine. There's nothing wrong with that. The book kind of writes it as kappa epsilon naught A over D. I'm not sure what's more significant than the other, but anyway, perhaps the other way is even a little more intuitive, which contradicts the book a little bit. That's not a big deal. The big thing is, guys, look at the mathematics and get an idea what's going on. So we're saying this is without a dielectric inserted. This is with a dielectric inserted. It's the same values, epsilon naught A over D. Epsilon naught A over D, yeah, but multiplied by a kappa, since there's a dielectric inserted. So it's a lot of the same math. They say a number of things, and I'm just trying to go in the order that they're doing it, you guys. And I do have some good, we'll see what we want to do. I mean, when we're actually doing this in class, some very interesting problems that are there. They tell us what are good assumptions to make, and then we just apply the mathematics and we get some really interesting conclusions. We'll do them in person whenever possible, but again, it is on film as well. And it's going to be films that are going to be like subsequent. Films that are already present, that I'm also going to put this film right next to those films as well. So we can look at that. Let me try to figure out where I want to go next with this, guys. We're almost there, guys. Hang in there. My big thing here okay. For some reason, I think I'm just not even finding the pages here. Okay, yeah, there's different things they say with the capacitors. I'm going a little different order than what they're doing in the book, but it shouldn't be too bad. Book's got some excellent examples. I mean, it's which is not surprising. It's an excellent book. They talk about the energy associated with a capacitor. What's the energy associated with anything? I mean, what's the energy associated with that very huge container of sand that we climbed up with, that we took a huge container of sand, sealed package, huge amount of sand, and we walked up We walked up 100 meters of a building and we're at the top of it. Well, what do we do? What's the energy associated with that? We gave it all that potential energy by doing all that work. The work required to do something will tell you how much potential energy is inside of it. The end kinetic energy will tell you how much potential energy was lost. Unless you threw it down, well, then you have to add the amount of kinetic energy that was initially present plus the change in potential energy, and you add the change in potential energy with the initial kinetic energy, and you get the new kinetic energy, which is a lot more. It's the change in potential energy, and you're throwing it down. Either way, it's a situation of where are you going, how difficult of a walk is it per step, and how many steps are you going to take? You know, how much work do you got to put into something to give it all that potential energy? There is potential energy associated with this capacitor. Why is that? Because if you hook it up, it's gonna fire out all these positively charged particles, 1.6 times 10 to the negative 19 coulombs for each one, let's say. 1.6 times 10 to the negative 19 coulombs for each of those charged particles. That's a lot of charged particles. Why? The charges are tiny. 1.6 times 10 to the negative 19, and let's say there's a billion of them. More than that, you know, whatever, a huge, huge number, trillions and trillions of them, and they come around. Well, how much work is done? Well, how much work did it take to get them there in the first place? Everybody was neutral in the beginning. These two things were neutral, and you took all the positive, you ripped all the positive charges that you could from here, and you loaded them over there. And that wasn't easy. In fact, initially it was really easy because there was no charges. You weren't having to, I didn't have to, if I'm a positive charge and I want to run over to that positive charge, you've got to push me, you've got to do work. True. If there's a lot of positive charge, you've got to do even more work. If there's a lot of positive charge over there and a lot of positive charge over here, for me to get over there, it's a lot of work you got to do. If there's just a little bit of positive charge over there, for me to get a positive charge over there is not that difficult. But if there's a lot of positive charge over there, the more positive charge that's over there, the harder it is for you to get there. You're ripping this thing off, the positive charges, you're having it come around here. Initially, there's nothing there. Nobody's repulsing you at that point. But the more positive charge you get on here, the more repulsion is taking place, the harder it is for subsequent movement of charge to take place. Initially, it's very easy. Toward the end, there's so much positive charge over there. You're fighting so much against positive charge that doesn't want you there. Initially, there's not much. I mean, it's almost like you set it up this way and say, oh, these are both neutral. Let me get positive charge over here. Well, that's easy. It was all neutral. The more positive charge is over there, the harder it is for you to get more positive charge over there. So there's a mathematical problem here. In the strictest sense, there's an integral there, to be honest with you. And that's where the energy of the capacitor comes in. So when you look at this, so let's see. Let's see what we can do. Let's erase a good amount of the stuff and see what we can do about it and kind of take it from there. There is, say a lot of things here. Okay, the way the book does it is different from a calculus type problem on the whole matter. But let's see what we can do. Let's try to look at this a couple different ways. Okay. It's a lot said, so let's see exactly what we want to do here, guys, how we're going to speak the language here. Like I said, the delta V and the V can kind of be synonymous. They have their, I guess they have their merits. I mean, but they said I can't help but mention that, yeah, Serway's got a good idea of the way they do stuff like this, guys. I can tell you, the way the book does. Let me try to abbreviate the way the book does it. Let me try to not do it foolishly. Hopefully, I can get this thing done right for you guys. Let's, so I can kind of bring this thing toward an end here and figure out what we're doing. You can basically say, if you're charging this thing up, you started, they were both neutral, and you got it to get all the way like that, right? And you connected it and everything else, and I said it wasn't easy to do. Well, yeah, you're darn right it wasn't easy to do. You got negative Q at the end of it, but you started with 0, 0. There was zero amount of charge. Charge is conserved, isn't it? Sure is. What's negative Q and positive Q? 0. Initially, they were both 0, 0. You just ended up getting a whole bunch of positive away from here, positive Q, which left you in a deficit right here and an abundance right here. Positive Q and negative Q does add up to 0. They were both neutral, but positive Q went all the way over there. And it kept getting more difficult. Kept getting more difficult. Let me try to go on the fly on this one, guys. Hopefully it works out okay for us. That's the same. The capacitance doesn't change. That's a constant, actually. What are you talking about? Well, there's not a lot of potential difference. If the potential difference is the greatest when you fully charge this thing. If you don't fully charge this thing and it's only a little bit, then there's only a little bit of Q. We'll say the positive Q. You only want one of the Qs, right? The negative Q or the positive Q, doesn't matter. But we'll say positive. You only have a little bit of Q if there's a little bit of delta V. When you add its maximum, let's say, or whatever, what for us is going to be its maximum, you got Q and you got delta V. If this is really big and that's really big, that's the same as really small divided by really small. The ratio, very small divided by very small, is the same as very medium divided by very medium, is the same as very large divided by very large. That C doesn't change for the circumstances. As long as the distance between the two doesn't change and the battery doesn't change and everything else, no matter how much charge is present, that holds up right here. If that's the case, it's a question of what's happening here. Is it true that a differential amount of work is equal to a small amount Q and a potential difference of V, whatever it may happen to be? I think there's kind of maybe a better way to look at this, and I think the better way to look at it is this is essentially, you guys remember that W was Q times V or Q times delta V. It's probably a better, that looks better to me than that, but that's neither here nor there. I got a better idea. If you want to go with this guy, let's go. Let's go. This is kind of the big picture. Is it true, if you multiply by delta V on each side, you got C delta V. Forgive me. No, wrong. If you multiply by delta V on each side, you got this. True. Here's where the other notation is a little bit better, actually, if you want to know the truth. There's a differential amount of work you got to do to move a differential. To do a small amount of work, you got to move a small amount of charge over a particular voltage. So, tell you what, this is true what I just said, but let's take it further. Multiply by delta V on each side, and then divide by C. multiply by delta V on each side, and then divide by C. The delta V and the V can be synonymous. There is a voltage, V, which is the same as delta V. This is however much is present in a particular location. So let's see here what the voltage would be. Voltage would be the amount of Q present, guys. I'm trying to actually speak. I'm trying to speak a couple languages here, guys. I'm not sure this is a good move, but this is Q over C. The argument, you don't have to know this, kind of know the result, you guys, but a differential amount of work that you would do, it's like a delta W, but it's more the calculus language on that, guys. And you've got a change in Q, which we'll call delta capital Q, and the potential difference, and that varies. Okay, time out. C is a constant. Q, the amount of Q that goes over there, what's Q initially? Big Q initially, my friends, big Q initially is zero charge. There was no charge over here. And then you kept adding charge. So this is kind of the move. That's the move. Watch out for those. I think so. I'm going with this. They say delta V. You could say one or the other. I could say that's the same as, delta Q. And then I could use the V. Watch out. The language occurs in books. I haven't seen every book that there is to see, my friends, but it occurs in numerous types of books. So it could be one or the other. Be aware of that when you do that. That's huge. This right here let's do it. Total work you got to do. The total work you got to do is the energy that's stored. Guys, if I did 100,000 joules of work to pick up that huge bag of sand 100 meters up in the air, those 100,000 joules of work is the potential energy. That is what's stored in the system. So this is the work that you're doing with this right here. This varies. I want to make that clear. It's kind of deceptive. I'm sorry. That's independent of the books, guys. Even the Serway book, there is an ambiguity there. That's independent of me using delta V or V. The Q, what do you mean by Q? Well, Q usually means some constant number at the end of it. In this case, it's a fluid dynamic process, which we could write in different ways, I guess. This is increasing from 0 to Q. I mean, at that point, I could probably use little q, honestly, to actually get the thing to work here. I don't want to keep changing this, guys. I'm probably getting people upset as is, so I don't want to go there. I just want to say, okay, he says Q. What's this Q thing? Okay. Well, it's some kind of integral like this. You can ignore this. Just look at the end result. C is a constant, my friends. So it's the integral of Q over C dq equals 1 over C, which is a constant, integral of Q dq from 0 to Q. I'm sorry I'm using the same one. Use it as Q final. Use Q sub F if you want, if it's an issue. At the end of the day, you guys, C is a constant. You integrate this, you got 1 over C, 1/2 Q squared from 0 to Q. It's equal to the work that you had to do is going to be the energy. The work that you have to do is going to be the energy stored in the capacitor. How did they write it? Let me just make sure. They write it as potential energy, which is true. Totally true. Potential energy, try to use their language exactly. Capacitor, potential energy of the capacitor, the work that we had to do. And it's going to be what? 1 over C times 1/2 times Q squared, evaluated this way. Well, that's going to be 0. That's just going to be Q. It's going to be Q squared if you plug in, my friends, all the stuff here. V equals Q over C. C equals Q over V. Now I'm using this. It's just a little easier to look at. You run through it a little bit faster. Be aware, it doesn't matter. Put a delta V there if you want. That's not a big deal. If you want to put this, if you want to put V equals Q over C, C equals Q over V, Q equals CV. If you plug in Q equals CV, Q equals CV, it becomes C squared, V squared. The C's cancel. You square Q squared, you're squaring the product CV. Squaring the product CV is C squared V squared divided by C is CV is 1/2 CV squared. Put in Q over C, we got CV, we got C is Q over V. C is Q over, you could also write here, C equals Q over V. Q over V, the V cancels. Q over V. Absolutely. That's kind of where they're going. They've got a good argument. Let me not beat this thing up completely. They got a good argument on this one that'll get you there without calculus. It's not that bad. It's not that bad. It's really good the way they do it. On page 550, they give a beautiful argument. You don't have to use calculus to get it. You still get it like the way they did it on page 550. In the end, it's essentially the same argument, you guys. But like I said, you can do it formally without any. All right. They talk about, let me kind of see here, guys. Kind of jumped around a little bit to get you there on some of these things, guys. Let me do a quick run at something else. It'll take us about another 10 minutes or so to get us there. They say different things. I kind of gave the argument already, how this stuff works out, why it's true, what's going on. Let me try to do a relatively fast discussion of how you evaluate, how you get an equivalent capacitance if capacitors are in a parallel arrangement, and how do you get an equivalent capacitance when capacitors are in a series arrangement. Two different scenarios, what's going on, how does that work, okay? So let's actually do that. Let's get some of this out of the way, and maybe I'll try to knock this out relatively quickly, at least write two scenarios here for you and kind of tell you what's going on. Write out the answer first, I guess you could say, as we do this. of what they are, so at least we have it. And then we, again, the book covers it really well. It should be pretty smooth. Wanted to talk about some of the harder stuff early. It's hard for there to be an early or a late in a long lecture, guys. To do justice to some of this stuff, I think we just need to talk a bit on it. When you go through these films, I mean, go through them as fast as you need to go with them and how you want, what you want to look at and all. But hopefully this works out for everyone. This is kind of the goal here. All right, guys. Capacitors. Capacitors. Forgot how to spell, guys. All right, capacitors in parallel and capacitors in series. I'll kind of give you I'll kind of tell you the end of the story first, and then we'll just tell you how we got to the end of the story. So capacitors in parallel. Okay. Kind of make a long story short, I guess you could say. The equivalent capacitance of N capacitors, let's say, capacitance equivalent of N capacitors, or however many capacitors you want to talk about, they write it like this. So I'll do what they do. That's the equivalent capacitance. So if you're looking about capacitors, if capacitors are in a parallel arrangement, like this, there's a lot of ways you can go here. Let me try to think. C1, C2. Capacitors looking like that, for example. That's a parallel arrangement. And if they're in series, you've got to be cognizant of the mathematics and be able to work with it and get it right. If they're in series, they look like this. And those, I'm trying to actually do this, guys. It's not a good drawing how I'll draw it another way. This is not a problem, but in case it is a problem, interpretation-wise, let me kind of write this a little different way. I'm worried more than I should be, but that's C1, that's C2, that's C3. I didn't put any capacitor here. So if you're looking at the book definitely draws better than I do. But if you look at a situation like this, something like that, C1, C2, C3, and looking at something like this, just drawing 3 of them, guys, but you know. Yeah, I could just kick myself. I mean, they drew it the same way I drew it initially. It's not a big deal. Let's just kind of leave it. That's more than fine, guys, except for what I just did. Let me see here. All right. So you're looking at this. All right. No great work of art, no matter what you do, but you got this right here, guys, and so where's that coming from? Where are they both coming from? You know, who knows? Let me see here. All right. The way you want to do this, the way it works out is this. When something's in parallel, there are let's say this thing is getting, it's a tough thing to explain sometimes, I think. Let's do what we can with it, I guess you could say. When something's in parallel, it becomes like one equivalent to what it would be like this. You know, 1 over, you know, it'd be just this guy, CEQ. That's what it means. What would it be if it was just one of them? Same thing with this thing. Well, I mean, this stuff goes pretty fast, pretty smoothly. Just get it started, I think. So let's talk about that. Well, the way the charge is, the voltage, the voltage across, the potential difference across all of these is going to be the same. If it's not, it'll arrange itself in such a way that the potential difference across these two plates, associated with C1 is equal to the potential difference across these two plates associated with C2, and it's equal to the potential difference across those two plates associated with C3. And this works for any number of plates that you have. So if that's the case, If the potential difference is equal, well, let me use V rather than delta V. Don't have to, but let's, use that, Do we know that C is Q over V? Yes. We know that C1 is Q1 over V1. C2 is Q2 over V2. C3 is Q3 over V3. Yeah, and for parallel combination going on, V1 equals V2 equals V3 equals some V. If that's the case, wherever you see V1, V2, V3, that's just V. And interesting. And if that's the case, the total sum, the total charge present is what's on C1, is what's on C2, is what's on C3. So I add these. Well, wait a minute. If you multiply by V on each side, you get Q1. If you multiply by V on each side, you get Q2. If you multiply by V on each side, you get Q3. This Q is Q1 is C1V, Q2 is C2V, Q3 is C3V. Wait a minute. Isn't, in general, if you multiply by V on each side, any Q is C times V. So there's an equivalent guy that will have everybody there. C equivalent times V. C times V will give me that big guy. That's C V1, C1V, C1V, C2V, C3V. Wait a minute here. There's a V. V, huh? Divide by V on each side. See, we said that C has this relationship to Q and V. Multiply by V on each side, you got the Q. Well, there is some equivalent Q, I guess, some imaginary Q, if you will. There's some, forgive me, there's a real Q composed of the sum of these and some sort of conceptual C such that if you were to go multiply by V on each side, Q equals CV. Well, there's got to be some equivalent mathematical CEQ times V. The mathematics will give me that Q. The Q is the sum of all these. Well, I got this. Why don't you divide by V on each side, my friends? Not bad. It works. It works. The only bad thing here, guys, I've run out of room in a sense, but okay, we can get it. All right, if that's okay, I mean, luckily you got the feature on the video. You can go back and we get what we want to get. So we got this. That is the proof. Now go the other way. Well, the other way is, okay, look, what kind of made this thing happen? What made this thing happen is there's an amount of charge, Q1 right here, a different amount of charge, conceivably, Q2, and a different amount of charge here, conceivably, Q3. Q1, Q2, Q3, there's an amount of charge Q1, an amount of charge Q2, an amount of charge Q3. All together, that's the total charge. Well, that total charge we'll have right here. And then that's your equivalent. Just do the math. See what happens here. The voltage across each capacitor was identical. All the voltages across each of the capacitors are equal to one another. There's different charges across each capacitor, more than likely. You add all those different charges together and you get one big charge. Well, from what capacitor would actually give you that one big charge? Well, I guess I have to find a value of C such that these guys, which are Q1 plus Q2 plus Q3, over that V, that'd give me that. Well, wait a minute, though. Q1 is C times V. Q1 is C1 times V. Q2 is C2 times V. Q3 is C3 times V. Altogether, you divide by V, it sums right here. Another way to look at it. Okay. Let's take it. Let's take it to the end, guys. The question, so this is the big thing. Voltages are equal across capacitors that are in parallel, but their charges add up. The charges are not the same. You have to add up the charge on capacitor C1 with the charge on capacitor C2 with the charge on capacitor C3 with the charge of with the charge on the next capacitor, however many capacitors you have. You have to add all the charges together to get one big charge. The voltages, however, when they're in parallel, the voltages, they spread out in such a way that the voltages are equal to one another across each capacitor. So V1, V2, and V3 are equal to one another. We'll just call it V. And then we did the mathematics that we did. Okay. Yeah. When they're in parallel, you're going to have to add up all the charges that are on each capacitor, but the voltages are equal across each capacitor when they're in parallel. When they're in series, the charges are identical. Why? Because there's only one hose, guys. The water goes through one hose. They are connected in series. Forgive me, when they're in series, I hope I didn't say parallel. When they're in series, when they are in series with one another, the charge amount is the same. If I load up 100 coulombs on one capacitor, I pushed over and loaded up 100 on the other and loaded up 100 on the other. They all go to the same place. I can't have just some over here. There's always like a chain reaction effect. Everybody's pushing each other around, and in the end, if I pushed 10 chairs this way, at the end, there's 10 chairs over there. If I keep pushing the 10, I don't acquire more chairs or lose chairs. Same thing here. There's this chain reaction effect. You get 100 coulombs on one of these. You get 100 coulombs on one of these, and bam, it pushes 100 coulombs away from here. So you got 100 coulombs on this thing, or whatever you did. I mean, you got 100 coulombs on this thing. You pushed 100 coulombs away from here. Now it's a negative 100 coulombs, and 100 coulombs went here. They pushed 100 coulombs went over here. There's going to be 100 coulombs at the end of it. So this is a different dynamic. When they're in series, Q1, forgive me, when they're in series, Q1 equals Q2 equals Q3. Yeah, you don't get more, you don't get less. When they're in series, the charges are equal. However, the voltages are different. Here the voltages add up. Before, the voltages were equal, but you had to add the charges in parallel. Voltages were equal, but you had to add the charges when they were in parallel. Voltages equal, but you had to add the charges when they were in parallel. When they're in series, the amount of charge, I got 100 here, and then I pushed 100 away from here and got them here. Then I pushed 100 away from over there, and the 100 got over here. It's 100, it's 100, it's 100. The same amount, but the voltages are different. The voltages add up to the master voltage. These got to be delta V1, delta V2, delta V3, delta V, or just V. I'm using the V rather than the delta V. Okay, you got to kind of be a little comfortable with that, hopefully. Okay, what's he talking about? Not much. C equals Q over V. C equals Q over V. Multiply by V on each side and divide by C. Multiply by V on each side. Multiply by V on each side and divide by C. Yeah, I make it sound like it's easy, and then I go ahead and proceed to make a mistake. C equals Q over V. I want to find out what the V's are, because I got to add them, you guys. What's V equal to? Multiply by V on each side and divide by C. There it is. All right. That's the general look. Really? Yeah. Well, all of these are the same. This guy's going to be Q times C equivalent. I don't know what that is, but it's going to be something. This V1 is going to be Q1 over C1. This one's going to be Q2 over C2. This one's going to be Q3 over C3. Boy, am I in trouble. No, I'm not. We already said it. We already said that C was going to be Q1 equal to Q2 equal to Q3. They're all equal to each other. And that's the big one. That's V. You got to add the V's together. Q1 equals Q2 equals Q3 equals Q. Here goes nothing. Pull a Q out of there. Get 1 over C EQ. Pull a Q out of here. Get this. Pull a Q out of all this. You know where this is going. Divide by Q on each side. You're looking at it. There it is. That's all it is, you guys. This is a lecture, I guess. This is a lecture from the Serway book, the Serway and Viewel book for the second semester course affiliated with electricity and magnetism for chapters 15 and 16, or topics 15 and 16. In short, from the Serway and Viewel book, this gives you a little bit of a synopsis of chapters. From the Serway and Viewel book, this gives you a little bit of a synopsis of topics 15 and 16. Hope it helps out. All right, thank you for your time. Take care.